Swayam Prabha. Digital India. Educated India.
Degradation pattern of textile effluent by using bio and Sono chemical reactor. Lecture number 27. Slowly now we are moving towards the end of this lecture series. But before we do that, we conclude we should also understand how Sono chemical reactors or biochemical reactors help in degradation of the textile effluent. For bioreactors, we have at least covered some portions, but in this lecture I have particularly dedicated understanding the Sono chemical reactor and its reaction mechanism. The degradation of textile effluent using a combination of biological and Sono chemical reactors involves harnessing the synergistic effects of both the processes to enhance the removal of pollutants from the wastewater. So, the ultimate aim is to remove the pollutants from the wastewater. Whichever strategy we adapt, whether we adapt traditional strategies or these advanced emerging technologies. Here is a breakdown of the processes. Biological treatment. In this stage, microorganisms are employed to degrade organic pollutants present in the textile effluent. The wastewater is typically treated in a bioreactor where microorganisms such as bacteria or fungi metabolize organic compounds into simpler, less harmful substances. This process is often effective for the removal of organic dyes, starches and other biodegradable compounds commonly found in textile effluents. Sono chemical treatment. Sono chemistry involves the use of ultrasound waves to induce chemical reactions in a solution. In the context of wastewater treatment, ultrasound waves can create cavitational bubbles in the liquid, leading to localized heating and the generation of highly reactive species such as the hydroxyl radical. These radicals are capable of oxidizing and breaking down a wide range of organic pollutants into smaller, less harmful molecules. So, it is now very clear and we have understood that biochemical or biological treatment requires the role of microorganisms and the enzymes that are secreted by them help, that is by bacteria and fungi, the enzymes that are present can metabolize the organic compounds present in the effluent into simpler and less harmful substances. Whereas, in Sono chemical reactor, what happens is that the ultrasound waves can create cavitational bubbles in the liquid, leading to production of hydroxyl radicals. And as I had told earlier also that these hydroxyl radicals are extremely reactive and can break down the organic pollutants to smaller and simpler, less harmful substances. Synergistic effect. Combining biological treatment with Sono chemical treatment can lead to synergistic effect that enhance the overall degradation efficiency of the process. What does the word synergy means? That the two together are combining and the collective effect is much more pronounced than their individual effect. So, that is where the synergistic effect becomes very, very important. The biodegradation of organic compounds that remain after biological treatment can be further degraded by sonochemical oxidation, while the sonochemical treatment can also help to break down complex organic molecules that may be resistant to biological degradation. So, what it means that whatever could not have been achieved by biological treatment could be attained by sonochemical reactors. Degradation pattern. The degradation pattern of textile effluent in a bio-hyphenated sonochemical reactor will depend on various factors, including the specific pollutants present in the effluent, the operating conditions of the reactors such as pH, temperature, ultrasound intensity and exposure time, and the type of microorganisms and ultrasound frequencies employed. Generally, the process will result in the breakdown of complex organic compounds into simpler, less harmful substances, ultimately leading to a reduction in pollutant concentration and improved water quality. So, what it means is that what is the degradation pattern? How does it all affect the breaking down of organic molecules, and what are the parameters that operate to help in this entire biosonochemical reactor mechanism? They are affected by pH, temperature, ultrasound intensity and the time duration of exposure. Generally, the process will result in the breakdown of complex organic compounds into simpler, less harmful substances, ultimately leading to reduction in pollutant concentration and improved water quality. So, the ultimate aim remains the same, that water quality should be improved, it should not have undesirable pollutants. Monitoring and optimization. Continuous monitoring of key parameters such as pollutant concentration, microbial activity and sonochemical activity is essential for optimizing the performance of the biosonochemical reactor system. Adjustment to operating conditions may be necessary to ensure maximum degradation efficiency and minimize the formation of harmful byproducts. So, ultimately, unless and until we are assured that the bioreactor part is working efficiently, the microbial activity is happening properly, whether the sonochemical activity is happening properly or not, it will not be able to decide whether the reaction is going on properly as per the desired mode. So, monitoring and optimization becomes very important. Overall, the integration of biological and sonochemical treatment methods offers a promising approach for the efficient degradation of textile effluent, contributing to the mitigation of environmental pollution associated with textile industry. Biological reactor for degradation of textile effluent. Now, let us look at it one by one. When utilizing a biological reactor for the degradation of textile effluent, the degradation pattern typically follows a series of biochemical processes orchestrated by microorganisms. Here is an overview of the degradation pattern. So, what exactly happens in a bioreactor? Hydrolysis. The first step in biological degradation involves hydrolysis, where large organic molecules present in the textile effluent are broken down into smaller soluble compounds. This process is facilitated by enzymes produced by the microorganisms. In the case of textile effluent, compounds such as starches, proteins and cellulose may undergo hydrolysis. So, in the first set, at the onset, there is hydrolysis, and this is facilitated by the enzymes secreted by the microorganisms. Acidogenesis. Following hydrolysis, the resulting small molecules undergo further degradation through acidogenesis. Acidogenic bacteria metabolize the soluble compounds produced during hydrolysis, converting them into volatile fatty acids, alcohols and other organic acids. This step generates intermediate that serve as substrate for subsequent stages of degradation. So, after hydrolysis, most of the components which were initially non-soluble become solubilized, and this solubilized situation, hydrolytic products, then undergo acidogenesis through the intervention of acidogenic bacteria, and they metabolize these solubilized components. Acetogenesis. We had learned these terms, but we will now look at it in a more elaborate manner. Just like acido, that is intervention of acid, this is aceto, which means in acetic acetogenic bacteria. The in acetogenesis, acetogenic bacteria further metabolize the organic acids produced during acidogenic genesis, primarily converting them to acetic acid, that is vinegar, and some simpler organic compounds. This process helps to stabilize the intermediate products generated earlier and prepare them for further degradation. So, by the intervention of acidogenesis and acetogenesis, there are different types of molecular fragmentation happening. Volatile fatty acids were formed in acidogenesis, whereas the same acidogenic compounds were then converted with acetogenic bacteria to acetic acid, which is nothing but vinegar. Methanogenesis. Methanogenesis bacteria play a crucial role in the final stage of biological degradation known as methanogenesis. These microorganisms utilize the simple organic compounds produced in previous steps to generate methane and carbon dioxide through anaerobic respiration. Methanogenesis helps to remove the remaining organic matter from the effluent while producing biogas as a byproduct. So, it is also an advantageous byproduct that is formed during methanogenesis. Removal of inorganic compound. While the focus of biological degradation is primarily on the organic pollutants, some inorganic compounds present in the textile effluent such as salts and heavy metals may also undergo precipitation, adsorption or biological uptake during the treatment process, leading to their removal or immobilization. So, although it is mainly focused, the biological reactor and the Sono chemical reactor are all focused on breaking down the organic pollutants, but as a side effect even the inorganic compounds and pollutants are also immobilized. Monitoring and optimization. Throughout the biological degradation process, parameters such as pH, temperature, nutrient level, microbial activity must be carefully monitored and optimized to ensure efficient and effective treatments. Adjustment may be made to maintain favorable conditions for microbial growth and activity, thereby maximizing degradation efficiency. Now, this is very important. If the microbes are not thriving properly, if they are not growing properly due to adverse pH condition or temperature condition, then what will happen, that the enzymes that are present in the 3 different types of bacteria which are present will get, their colonies will get affected, they will die out. If they die out, then neither acidogenesis will take place nor acetogenesis will take place, or nor methanogenesis will take place. Therefore, their optimization is very essential. Overall, the degradation pattern of textile effluent is a biological reactor, involves a series of connected biochemical processes driven by microbial activity. Through these processes, complex organic pollutants are progressively broken down into simpler, less harmful compounds, ultimately leading to the remediation of the effluent and reduction of environmental impact. So, what it means is that these are all connected reaction system, they are interconnected and they are driven by the microbial activity. So, through these processes, complex organic pollutants are progressively broken down one by one into simpler, less harmful compound, and finally, by anaerobic digestion they are converted into methane and carbon dioxide. So, in a way it is complete mineralization, or sometimes some fatty acid or acetic acid, that those kind of very low carbon containing acids which are soluble in water are produced. Moving on, there are benefits of degradation pattern of textile effluent using bioreactor, and this we had seen fleetingly in one of the lectures. We will do it in a little more detail to see what are the benefits. We have been talking so much about benefits of every process, mitigating process. Let us also understand this. The degradation of textile effluent using a bioreactor offers several significant benefits. Environmental friendliness. Bioreactors employ natural processes mediated by microorganisms to degrade organic pollutants in textile effluent. Unlike chemical treatment methods, which often involve the use of harsh chemicals and generate toxic byproducts, biological degradation is environmentally friendly and sustainable. Biodegradation of complex pollutants. Textile effluents contain a diverse range of organic pollutants, including dyes, starches, cellulose and other complex organic compounds. Bioreactors are highly effective at degrading these complex pollutants into simpler biodegradable compounds through enzymatic processes mediated by microorganisms. So, microorganisms, they give out enzyme. These enzymes work on the organic pollutants to degrade them, and that is how these are biodegraded with the help of these microorganisms into simpler molecules. Most effectiveness and cost effectiveness. Biological treatment methods typically have lower operating and maintenance cost compared to chemical treatment processes. Bioreactors require minimal energy input and rely on naturally occurring microorganisms, reducing the need for expensive chemicals or infrastructure. So, this process is highly cost effective. Versatility and flexibility. Bioreactors can be tailored to treat a wide range of textile effluents with varying composition and pollutant loads. The microbial communities within the reactor can adapt to different environmental conditions and pollutant concentration, providing flexibility in treatment operation. So, they are highly flexible and versatile, and this we have learnt in one of the earlier lectures. Reduce sludge production. Unlike chemical treatment methods, which often produce large volumes of sludge that require further disposal problem and treatment, biological degradation results in conversion of organic pollutants into gases, mainly as carbon dioxide and methane and water. This reduces the production of sludge and minimizes the need for sludge management, and this we had studied in that lecture where we had discussed about the sludge management of the textile effluents. So, one sees that it is cost effective, it is versatile, it is flexible, and now it is also much lower in sludge generation, or practically after the mineralization of the organic pollutants, only gaseous material are exuded out. Potential for resource recovery. In addition to pollutants removal, bioreactors offer the potential for resource recovery from the textile effluent. For example, methane produced during anaerobic digestion in bioreactor can be captured and used as renewable energy source, offsetting energy cost associated with wastewater treatment. So, what it means that, remember, we have been talking about resource recovery for a while now, and any process which can give something beneficial out of the degradation process from the sludge formation, which is a major problem. If we get biogas, that biogas can be used or utilized in the more effective manner as renewable energy source. So, it would be an advantageous situation to use bioreactors, especially under anaerobic digestion conditions. Compliance with regulation. Many countries have stringent regulations governing the discharge of wastewater from industrial facilities, including textile manufacturing plants. Biological treatment methods can help industries meet regulatory requirements by effectively removing pollutants from effluent and ensuring compliance with environmental standards. Public perception and corporate responsibility. Adopting environmental friendly wastewater treatment technologies such as bioreactors can enhance the public perception of textile manufacturers and demonstrate corporate responsibility towards environmental stewardship. This can improve brand reputation and foster goodwill with customers, investors and regulatory authorities. Now, obviously, if we have a comparison between two factories and their owners, one factory is indulging in all these emerging technologies for the remediation and mitigation of pollutants. Another factory is using traditional methods of mitigation. Obviously, the sludge amount that is generated will be enormous in the second case, and they are now not worried, or rather it will be cost effective. Sludge management will become another big problem for the second industry situation. So, in such a case, when the first one is doing all the good practices, the customers, the stakeholders, the government agencies are all in praises of that company, which shows that the public perception of that textile manufacturer becomes very high, and shows that he or she has corporate responsibility towards environmental stewardship and sustainability. Overall, the degradation of textile effluent using bioreactors offer a sustainable, cost effective and environmentally friendly solution for wastewater treatment in textile industry, contributing to pollution prevention and resource conservation efforts. Now, what is the degradation pattern of textile effluent by using Sono chemical reactor? And this we have not discussed earlier. So, let us try to understand, because this chapter has been dedicated, or this lecture has been dedicated mainly to bioreactors and Sono chemical reactors. When employing a Sono chemical reactor for the degradation of textile effluent, the degradation pattern is primarily driven by Sono chemical reaction induced by ultrasound waves. Here is a breakdown of the degradation pattern in a Sono chemical reactor. Cavitation. The key mechanism in Sono chemical degradation is cavitation. Ultrasound waves create cavitation bubbles in the liquid medium by rapidly changing the pressure. These bubbles grow until they collapse violently, generating a localized hotspots of temperature reaching several thousand degrees Celsius and pressures exceeding 1000 atmosphere. It is as high as that, but it is invisible. This phenomenon leads to the formation of highly reactive species such as hydroxyl radicals, hydrogen peroxide and other reactive oxygen species ROS. Oxidation. The reactive species formed during cavitation reaction are extremely potent oxidizing agent. They react with organic pollutants present in the textile effluent, initiating oxidation reactions that break down complex organic molecules into simpler, less harmful compounds. This oxidative degradation process targets various organic pollutants including dyes, surfactants and other organic contaminants commonly found in textile wastewater. So, what it means is that this whole process is very sleek. Oxidation is happening due to the generation of oxidative species which are being created by the cavitational bubbles. The cavitational bubbles grow in size and then violently explode, increasing the localized temperature and pressure to be very high, where these species are generated in situ. And then they are so reactive that they immediately attack the pollutant and break it down. Mineralization, sonochemical oxidation ultimately leads to mineralization of organic pollutants, converting them into inorganic products such as carbon dioxide and water and mineral salts. This process represents the complete degradation of organic pollutants, resulting in their transformation into harmless substances that can be safely discharged or reused. So, you see that this is a very safe process and there is complete mineralization of the organic pollutant. Degradation efficiency. The degradation efficiency of sonochemical reactor depends on several factors, including ultrasound frequency and intensity, reactor design, temperature and pH, and the concentration and nature of organic pollutants in the textile effluent. Optimization of these parameters is essential to maximize degradation efficiency and minimize the formation of harmful byproducts. So, what it means that these are very well designed machines, reactors, but we have to keep certain parameters into mind, and unless and until it works on those parameters, the sonochemical reactor efficiency may not be able to be achieved. And what are these several factors? It includes ultrasound frequency and intensity, reactor design, temperature, pH and concentration and nature of the organic pollutants present in the textile effluent. Synergistic effect. In some cases, sonochemical degradation may be combined with other treatment methods such as advanced oxygen processes AOPs or biological treatment to enhance overall degradation performance. These synergistic approach can be leveraged the strength of each of the treatment method to effectively remove a wide range of pollutants from the textile. So, what happens that if sonochemical reaction is combined with either biological system or any of the advanced oxidation system like Fenton reaction or hydrogen peroxide UV and those kind of reactions with ozone, then it can further enhance the degradation of the organic pollutants. Monitoring and control. Continuous monitoring of key parameters such as pollutant concentration, sonochemical activity and the formation of intermediates and byproducts is crucial for optimizing the performance of sonochemical reactors and ensuring efficient degradation of textile effluent. Control strategies may involve adjusting operating conditions and reactor configuration to achieve the desired treatment objectives. Overall, sonochemical reactor offer a promising approach for the degradation of textile effluent by harnessing the powerful oxidative capabilities of ultrasound induced cavitation reactions. By effectively breaking down organic pollutants into harmless end products, sonochemical treatment contributes to the remediation of textile wastewater and the protection of environmental quality. So, what it means that it is a very promising approach for the degradation of organic pollutants, and by effectively breaking down organic pollutants in a very harmless end product, sonochemical treatment has an edge over many other such new strategies which have been developed. and therefore, it contributes to the remediation of textile wastewater and protection of environmental quality in a big way. Benefits of degradation pattern of textile effluent using Sono chemical reactor. The degradation of textile effluent using Sono chemical reactor offers several significant benefits. Efficient degradation of complex pollutants. Sono chemical reactors utilize ultrasonic waves to generate highly reactive species such as hydroxyl radicals, which are capable of rapidly degrading complex organic pollutants present in the textile effluents. This results in efficient removal of various organic compounds including dyes, surfactants and other recalcitrant pollutants. So, what it means that it is very efficient in breaking the toughest of the organic pollutants also, because of the generation of the hydroxyl ion and hydroxyl radical, which is extremely reactive, and this generation of hydroxyl radical takes place by the cavitational effect. Rapid treatment process. Sono chemical degradation reactions occur rapidly, typically within seconds to minutes, allowing for a quick treatment of textile effluent. This rapid processing time can increase treatment capacity and throughput, making Sono chemical reactors suitable for industrial scale application with high wastewater volumes. That means, even on a very large scale, these can be applied, because many a times, as I told you earlier, that large scale up on the industrial scale sometimes does not work as efficiently as what it was developed as in the laboratory. So, Sono chemical is one such method which is very rapid, it happens within seconds and minutes, whereas we have seen that many of these mitigation technologies require several hours, sometimes even 24 hours for the reaction to get completed. No chemical additive required. Now, this is again a big advantage, that unlike traditional chemical treatment method, where chemicals are dosed into it and then coagulation, flocculation takes place, Sono chemical reactors do not require the addition of chemical oxidants or coagulants to facilitate pollutant degradation. This reduces the need for handling and storage of hazardous chemicals and simplifying operation and maintenance procedure. So, definitely it has again one more feather to its cap. Versatility and adaptability. Sono chemical reactors can effectively treat a wide range of textile effluent with varying composition and pollutant loads. The treatment performance can be adjusted by controlling parameters such as ultrasound frequency, intensity and exposure time, allowing for customization of specific wastewater characteristic. Minimization of sludge production. Sono chemical degradation primarily leads to mineralization of organic pollutants to carbon dioxide and methane, converting them into simpler, less harmful compounds such as carbon dioxide, methane and water. This minimizes the production of sludge compared to biological treatment methods, reducing the burden of sludge management and disposal. So, this also is an added advantage. Enhanced removal of persistent pollutant. Sono chemical reactors are particularly effective at degrading persistent organic pollutant, that is the POPs, which are very tough to degrade by other methods, and emerging contaminants that are challenging to remove using conventional treatment methods. The generation of highly reactive radicals during sonochemical reaction ensures efficient degradation of even the most recalcitrant pollutant. So, even the toughest of tough organic persistent pollutant can be broken down by these very powerful hydroxyl radicals created by sonochemical reactor using the ultrasound waves. Energy efficient. Sonochemical reactors typically require lower energy inputs compared to thermal treatment methods such as incineration. While ultrasound generation does consume energy, the overall energy consumption of sonochemical treatment is relatively low, especially when compared to the energy intensive processes of heating and maintaining high temperature. So, here the overall energy consumption also is low, because the sonicator works at a very low voltage, but because it generates ultrasound waves, and it is these waves that are actually responsible for making bubbles and the cavitation process of generating these bubbles which grow up and which eventually explode violently. Compliance and regulation. Sonochemical treatment can help industries meet regulatory requirements for wastewater discharge by effectively removing pollutants from textile effluent and ensuring compliance with environmental standards. This can mitigate potential fines and penalties associated with non-compliance and improve the company's environmental performance. Overall, the degradation of textile effluent using sonochemical reactors offer a rapid, efficient and environmentally friendly solution for wastewater treatment in textile industry, contributing to pollution prevention and environmental sustainability efforts. Textile effluent degradation through other methods. What are the various methods that can be adopted for one major factor, how to break down the persistent organic pollutants of the textile effluent? The textile effluent degradation can be approached through various means, each with its own advantages and limitation. Here are some of the common examples. Biological treatment. Just a while ago, we studied about the biological treatment along with sonochemical treatment. This involves using microorganisms to degrade organic pollutants present in the effluent. Techniques like activated sludge processes, bio-trickling filters and constructed wetlands utilize bacteria, fungi and plants to break down contaminants. Biological treatment is eco-friendly and cost effective, but may require longer retention times and can be affected by variation of pH, temperature and nutrient levels. And this we have learnt just a while ago, that it is a long drawn process, but it is effective, hence it is practiced. Chemical oxidation. Chemical oxidants like hydrogen peroxide, ozone and chlorine dioxide can be used to oxidize organic compounds in textile effluent. These chemicals react with pollutants to break them down into less harmful substances. Chemical oxidation is effective for treating complex organic compounds, but can be expensive and may generate hazardous byproducts. advanced oxidation processes. Now, we are consolidating most of the technologies that are being practiced in the textile effluent mitigation, and we just saw that biological treatment or chemical treatment, and now we are proceeding to advanced oxidation processes. You may find it as an repetition, but here we are consolidating in this lecture all the possible methods along with sonochemical method. AOPs involve the generation of highly reactive hydroxyl radical to oxidize organic pollutants. Techniques such as Fenton reaction Fe2 plus hydrogen peroxide, photofenton reaction Fe2 plus hydrogen peroxide and UV, and photocatalysis using semiconductors like titanium dioxide are used for these processes. AOPs can be efficient in degrading a wide range of organic pollutants, but may require UV light source and catalyst, making them energy intensive and costly. So, now we are trying to see which one is better than the other one, which is cost effective, which is energy intensive, and what are the sludge situation that each one of them generate. It is a kind of a comparative analysis of various methods that we have discussed. Adsorption. Adsorption involves the attachment of pollutants to a solid surface such as activated carbon or other adsorbents. Textile effluent can be treated by passing it through adsorption column or beds containing these materials. Adsorption is effective for removing organic dyes and other contaminants, but may require frequent regeneration or replacement of adsorbents. Membrane filtration. Techniques like ultrafiltration, nanofiltration, reverse osmosis, we have discussed this before. Use semi-permeable membrane to separate pollutants from water. These methods can effectively remove suspended solids, dyes and other contaminants from textile effluent. Membrane filtration is energy intensive, but produces high water quality treated which is suitable for reuse and discharge. So, there are advantages, there are disadvantages. It requires a lot of energy, and then there is a problem of membrane fouling that cannot be avoided. Electrochemical treatment. Electrochemical method like electrocoagulation or electrooxidation use electric current to destabilize and degrade organic pollutants in water. Metal ions generated during electrocoagulation can coagulate and precipitate contaminants, while electrooxidation produces reactive species that oxidize pollutants. Electrochemical treatment can be effective for removing color, COD and other pollutants, but they may require high energy consumption and electrode maintenance. So, most of them are energy intensive processes, as you will learn by now. Hybrid system, combining multiple treatment methods such as biological with chemical or biological with physical or chemical with physical processes can enhance treatment efficiency and reduce cost. Hybrid systems can capitalize on the strength of different techniques while mitigating their weaknesses, offering a more comprehensive approach to textile effluent degradation. So, what does it mean? That hybrid systems, that we use a combination of biological with chemical or biological with physical, or chemical with physical. This kind of combinations can reduce the cost and can also reduce the energy consumption and yet be effective enough to remove the pollutants. Each degradation method has its own sets of advantages and challenges, and this we have seen in all the lectures that we have had so far. And the most suitable approach depends on factors such as the composition of effluent, regulatory requirement, treatment objectives and available resource. We cannot carry out a Sono chemical reactor if the textile manufacturing unit does not have a sonicator. We cannot carry out a chemical reaction if there are no bio filters or if there are no constructed wetlands. So, depending on the resource that is available, all these mitigation plans can be made. Textile effluent can also go through a lot of degradation. By recommending these degradation pattern, the textile effluent typically involves a combination of treatment techniques, and we have seen that preliminary treatment, primary treatment, secondary treatment and tertiary treatment as different stages of treatment for different types of organic pollutants. It typically involves a combination of treatment techniques to achieve comprehensive removal of pollutant, and here is a recommended pattern. First is the preliminary treatment. This involves the removal of large solids, grit and debris from the textile effluent through physical processes such as screening and sedimentation. Primary or preliminary treatment helps protect downstream processes from clogging and damaging. Biological treatment, employing biological processes like activated sludge, biofilters or constructed wetlands to degrade organic pollutant present in the effluent. Biological treatment is effective for reducing organic contaminants, including dyes, and can be environmentally friendly and cost effective. Advanced oxidation processes AOPs follow biological treatment with advanced oxidation processes like Fenton's reaction, photofenton's reaction or photocatalysis to further degrade recalcitrant organic compounds. AOPs originate from highly reactive hydroxyl radicals that can oxidize a wide range of pollutants, enhancing the overall treatment efficiency. Membrane technology and membrane filtration we have studied quite in detail, that membranes filtration produce high quality water suitable for reuse and safe discharge. Disinfection, apply disinfection techniques like chlorination, UV radiation or ozonation to eliminate pathogens and ensure microbial safety for the treatment of effluent before discharge or reuse. Disinfection helps meet regulatory requirements for protecting the public health. By combining biological treatment, advanced oxidation processes, membrane filtration and disinfection, this degrades pattern addresses various types of pollutant present in the textile effluent. Additionally, it provides comprehensive and environmentally sustainable approach to effluent treatment, meeting regulatory standards and promoting water use and conservation. So, we have seen that most recommended is biological treatment, advanced oxidation processes, adsorption and microfiltration. All these are most recommended for degradation method of textile effluent. Moving on, disinfection is also equally important, and which is achieved by UV radiation or ozonation to eliminate pathogens and ensure microbial safety, because the microbe colony which is actually working for the degradation of organic pollutants should not get contaminated. By integrating biological treatment with advanced oxidation processes, adsorption, membrane filtration and disinfection, this degradation method provides a comprehensive and effective approach to treating textile effluent containing dyes. It addresses a diverse range of dye pollutants present in textile wastewater while ensuring compliance with the environmental regulation and promoting water reuse and conservation. So, the whole idea is how to make the wastewater safe enough to be reused or to be discharged in water bodies. So, degradation of surfactants also we have seen quite in detail. So, I will skip this, and adsorption and membrane filtration are processes which have been already practiced for the application or degradation of surfactant. Here also, by integrating the biological treatment, advanced oxidation processes, adsorption, membrane filtration and disinfection, this degradation method provides a comprehensive and effective approach to treating textile effluents containing surfactants. Ozonation. Ozonation we have spoken quite in detail that bio-treated fabric wastewater can be more dangerous than the untreated discharge, as certain colors are changed into little natural atoms. In this manner, further treatment is mostly required, and especially utilization of ozonation as short post treatment after the natural procedure can be gainful for breakdown of refractory mixes and evacuation of poisonous quality of material wastewater, yet observing mutagenicity and harmfulness is a significant apparatus and ought to be utilized to supplement ordinary examinations. Phytoremediation. This also we have dealt in a lot, that many of the roots of microflora can be used for the remediation. Phytoremediation has advantages such as being solar energy dependent and has an aesthetically pleasant method of treatment. Moving on to microbial biotechnology, we have dealt a lot in detail about this, and we know that enzymes, for example, azoreductase, laccases, lignin peroxidases, manganese peroxidases, reductases, tyrosinases are all responsible for accounted for engaging into the breakdown of azo dyes by the help of these microbes. In conclusion, we can say that primarily the preliminary treatment, biological treatment, advanced oxidation processes, adsorption, membrane technology and disinfection are all very much responsible. So, to conclude this lecture, I would say that a concerted effort is needed to plan the mitigation plan, and according to the number of or types of organic pollutants that are present, one has to strategize which mitigation route has to be adopted. But definitely sonochemical method is one of the best, and that is what is the learning lesson from this lecture. So, with this we have come to an end of this lecture. Thank you.